Okay, today we're going to have a look at finding the equation of a function if it's in one of our special forms, which is our a, h, and k form. Our a, h, and k form. That is, if we have it, if it's factorized so that we can very easily see the dilation factor, so we can very easily see the horizontal translation factor, and so we can very easily see the vertical translation factor. This particular method won't work if we have a polynomial in expanded form. It will only work when we have it in that special factorized form where we have AH, where we can see AH and K. Just to start with, the first example we're going to have a look at is if we can see the special point, and if we can see the point that's one step to this across from that special point. So I'm going to start off by drawing a cubic function. It can be any old cubic function. This works exactly the same with hyperbolas, works exactly the same with square root functions, exactly the same with parabolas. Okay, it's the same ideas. So just so we've got our special point here. So in a cubic function, that special point is called the point of inflection. And then if we were to have another point that's one step away from that point of inflection. This is an example for when we know a point that's one step away from that point of inflection. Because we know when we're sketching functions of this kind that if we go across one, then we have to go up a. So if we've got a point that's one step to across from the middle point, we can see A as well. So let's just have a bit of a go. Let's just say this point of inflection is at 2, 2, and this point here is at 3 and 2.5. So you see here, this 3, it's one across on the x-axis from the point of inflection. So this particular method will only work when we're one across from the special point in a cubic function. That's the point of inflection. So when we've got the point of inflection, we always know, that's 2, 2. If you've got that special point and that point of inflection, we know straight away what h is. It's the x value. We know straight away what k is, which is the y value. So in this particular value, we know h and k straight away. Now, because we have a point that's one step away from the middle point, the center point, we can also see A because we always step across one and step up A. So therefore, A in this case equals a half, or 0.5. So therefore I say to myself, we write down the general form, and I look at the function and go, well, that's a cubic function. So I need to think about the general form of a cubic function, which is y equals a x minus h cubed plus k, and then all I have to do is fill it in. A is a half, so I'm going to actually put that on the bottom, but if you wanted to write multiplied by 0.5 at the front, that would be fine. All over 2. Here we go. And that's how you'd find the equation if you were to have the special point, the point of inflection, and a point that's one step across from the point of inflection. So let's have a look at a second example where we know the point of inflection, but we don't necessarily know a point that's one step across from the point of inflection. So let's have a look. Now this is a square root function. Square root function. Now its special point isn't called a point of inflection. I've just been calling it the starting point. Starting point. So our starting point for this square root function is 2, 2, and I've given us a point down here which is at 6 and negative 4. 6 and negative 4. So straight away we know that my special point gives us the h and k values. I know that the h value is the x value. I know that the k is the y value, so I know h and k. I know it's a square root function. So I know the general form of a square root function is y equals a square root of x minus h plus k. Okay, and I know that from my starting point, I know h and k, so I'm going to fill that in. So I get a x minus 2 plus 2. So that's like halfway there. Then we say to ourselves, okay, we've got another point. We've got this other point, which is 6 and negative 4. So if we substitute that into the equation for x and y, that allows us to solve for a. So instead of writing y, I'm going to write negative 4 equals a square root of 6 minus 2 plus 2. And then all I have to do is rearrange. So I get negative 6 equals a square root of 4. Square root of 4 is 2, so negative 6 equals 2a. So therefore a equals negative 3. So therefore, finally, my final function is negative 3 times the square root of x minus 2 plus 2. I hope that helps with finding equations of functions where we can see them in the factorized form and the a, h and k form. If you want any other examples, just let me know. We'll be working on some more of these in class. So let me know how this feels and if you need any more help. Okay. Talk soon. Bye.